Okay, so welcome back, grade 11s and 12s. So we are going to start a new unit now in chemistry, and this will probably be our final unit for the year as we go through. We're going to go through solutions, we're going to go through some acids and bases, then as well as concentration. And that's really important for any of you who are thinking about maybe going into nursing. We have to go through how to figure out concentrations of different things. So we're going to start with today is just kind of an introductory kind of slideshow. We're going to kind of go through some terminology that you need to be able to use when you're describing solutions. And we often kind of think of solutions as mostly liquids, and you are right, most of the time they are liquids, but you can have solid solutions as well as gas solutions as well. Okay. So let's go through solutions, kind of an introductory, and really this kind of lecture focuses on really just terminology so that we can talk appropriately when we're describing solutions. So why is this important? Well, from our last unit, okay, this is one of the reasons. From our last unit, a process engineer would create a process that, say, produces HCl. So say you want to produce like, let me just get my writer here. Say you wanted to produce like 100 grams. Wow, it shows a really brutal color there. So you want to produce 100 grams of HCl, okay? And that was 100 grams of NABR. And HCl is what we call a waste product. So it's a product that you want to get rid of, okay? You were trying to make NABR and it's just HCl was made, and you have 100 grams of it and you're trying to get rid of it. Now remember, our last unit, stoichiometry, would kind of tell you if you're going to make 100 grams of HBr, this is how much HCl you'll make, and if you don't want the HCl, that's how much you have to get rid of. Okay? So that's what kind of our last unit taught us. Well, now, this next unit dealing with solutions is going to lead us into how we get rid of this. So if we had all this HCl and we're like, we got to get rid of it somehow, and you can't just throw it down the drain, okay? You have to pay people to do it. Well, when you pay people to do it, what are they actually doing? Well, waste disposal is a major concern and cost for companies. When you actually produce something, it's a big problem when you have waste products. So to get rid of the HCl, we can neutralize it with an acid or a base. Or we could dilute the concentration of the HCl to a safe level. We can add so much water to it that the HCl becomes so dilute that then you could actually just kind of throw it away. Now, in order to do this, to do either of these, we have to know about solutions. So if we want to solve this problem of getting rid of the HCl, we're going to have to learn about solutions in this unit. So that's one of the reasons why we have to go through this. As well as really important with solutions, and this is in particular with nursing, is making sure that your concentrations are properly. Anything, almost any product that you have can be deadly if it's too concentrated or if it's potentially too dilute and it doesn't do its effect. Most of the time it's more of being too concentrated and causing like an overdose on something. So drug overdoses are one of them, where it can be usually they're accidental, but taking something that's too concentrated can cause you to die. Now, some people do this with illicit drugs, but they also do it sometimes accidentally in the medical field, where a nurse or a doctor accidentally screws up in their calculations, and they provide someone too much medication, or in the rarest times, they also sometimes give them too little of medication, and it doesn't treat their symptoms. So we have to know, well, how do you prepare these concentrations? So an example would be something like aspirin. Aspirin's pretty safe, but if you take too much aspirin, you can actually cause death. So you have to make sure that you're taking it in the proper concentrations. Okay? Another example, when people make baby soap, okay, they have to make it a little bit less concentrated than soap for adults because baby's skin is more sensitive. So chemists would be responsible for determining, well, how concentrated is that baby shampoo going to be, and to ensure that it doesn't have any effect on the skin. So overall, regardless of what you're talking about, in order for solutions to be safe, okay, they must ensure they have the proper, what we call concentration. And this is going to be a huge term that we're going to be talking about as we go through. So making sure that they have the proper concentration. They're not too strong, they're not too weak. Okay, and we're going to kind of clarify what that term means coming up. So we're going to go through some essential terminology now. The rest is going to be kind of just going through and saying, well, what are these different terms? Well, the first thing we need to know is, well, what is a solution? Okay, this is the title of the unit. What is a solution? Well, a solution is what we call a homogeneous mixture. Now, this word homogeneous means that it's the same all the way through. You can't tell that there's a bunch of different things in here. So when we look at orange juice, there's a whole bunch of different molecules inside, but you can't tell where one molecule ends and the next one starts. Okay, it's called a homogeneous mixture. It's very different than something like a pizza, which is a heterogeneous mixture, because you can see where, the different molecules, you can see pepperoni ending and cheese starting. But in solutions, you can't do that. Everything looks exactly the same throughout. So here's another example of solution: steel. So what steel is, it's an actual metal solution, or a solid solution, which we sometimes forget actually exists. So what steel is about 95% iron, okay, and then it's about 10 to 5% carbon. So iron rusts pretty rapidly. So what they do in order to reduce its rusting is they actually put a little bit of carbon in there and they make a solution. So you can't really see where the carbon ends and the iron begins, but that's what steel is. It's just a combination of iron and carbon, and it's more resistant to corrosion. Okay? The other thing we have is air. Okay, it's also a solution. So in air, you're going to have O2, you're going to have N2, you're going to have CO2, you're going to have some of the noble gases in there, but you can't really see where all the different ones are. So that's what a solution is. It's basically, there's a whole bunch of different molecules in there, but we don't know where they are. They're all kind of mixed together perfectly. Now, the big thing I want you to get from this is everyone always knows solutions can be liquids, but we don't want to forget that solutions can also be a solid or a gas. So steel over here, which I'm highlighting, is a solution. Air over here is a solution. Okay. Now, the other thing about solutions is it's what we call a variable composition. Okay? So this is kind of a fancy term for basically saying that when we look at, say, orange juice, we can have a really concentrated form of orange juice, or we can have a really dilute form of orange juice. It's still a solution, but we can have it really concentrated, or we can have it dilute. When we look at the air, we can have really high concentrations of oxygen and low concentrations of N2, or we can do the opposite, where there are high concentrations of N2 and low of O2. And same with this. We can use 5% carbon or 10%. So that just means that it's a variable composition. It means that we can kind of change the solution slightly by changing how much of each component is in the mixture. Okay, so now, what a solution is a combination of two things, a solvent and a solute. So let's talk about the first one. It is a solvent. What a solvent is any substance that has the other substance dissolved in it. So most of the time, this is going to be water. Okay, the way you can kind of look at it is that it's the substance that's in the largest amount. So when we look at steel, steel is a solution, okay, but it's mostly iron with a little bit of carbon. So therefore, iron, because it's in the largest amount, it's 95% iron, it's considered the solvent. And what you've done is you've dissolved carbon into iron. So we call it the solvent. Okay. Solute is a little bit different. Okay, so solute is the substance dissolved in the solvent. It's the one that's present in the smaller amount. Okay, you're going to mix two things together, and they're very rarely going to be in equal proportions. So whatever the largest amount is the solvent, and the smaller amount is the solute. So when we look at steel again, since it's mostly iron with a little bit of carbon, with a little bit of carbon would be considered the solute, and iron would be the solvent. Okay, now, like I mentioned before, almost all the time, water is acting as a solvent, at least when we're talking about liquids. Okay? And because it happens so often that water is the solvent, we call it something special. We call it an aqueous solution. And all an aqueous solution is, and you may have seen this earlier on in the unit when we were doing skeleton equations, and we would write something like, let me pick a better color here, something like this, AQ. Okay? That means aqueous solution. So it would be something like, if I wrote something like NaCl, AQ, all that means is that I've taken sodium chloride, an ionic compound which is solid, and dissolved it into water. And we could call it NaCl aqueous. If you don't have the aqueous there, then you're talking about the solid form of sodium chloride. So aqueous solution just means that water was acting as the solvent in the case. So anytime that you've dissolved something in water, it's an aqueous solution. So orange juice is an example of one. You took the solute, which is the juice concentrate, so kind of that really, really concentrated form, and then you dissolved it in water, acting as the solvent, and now orange juice is considered an aqueous solution. All right. So I just kind of wanted to go through just all the different types of solutions. I'm not going to really focus on this because you don't have to know all of these things, but just showing, we always think of solutions as liquids, but we got to kind of keep in mind that there's also gas. So you can have two gases dissolved together. An example of that would be like air. Okay. Another example of a solution is like pop or soda. What they've done is they've taken gas, CO2, and they've dissolved it into liquid. Okay, so the solute present in smallest amount is CO2, and they dissolved it mostly in water. Okay, carbonated water. That's what carbonated water is, CO2 dissolved in water. Okay, so that's a solution. Okay. Sometimes we take a gas and we put it into a solid. So that's what you sometimes do with like styrofoam as an example of that. Also some hydrogen in gold. So we take hydrogen gas and we put it into gold and it makes it appear bigger. You can have a liquid dissolved into a gas, and that would be like water vapor. I'm not going to go through all of these, but there's a lot of different types of solutions. I'll take a look at the last one because we don't talk about these really in chemistry very often. Alloys is when you take two metals and you dissolve them together, and that would be like a metal alloy. Okay, and they do these sometimes to create some really cool metals. All right, some more terminology. Another term is miscible. So what miscible means is when two liquids are able to dissolve in each other. So an example would be like if you take ethanol and water, okay, they can dissolve in each other. If you put these two things together, you're not going to have a layer of ethanol and then a layer of water. Okay, you're going to have them all mix. Okay, so the ethanol and the water is not going to be like two different layers like this. It's all going to be mixed together, and you're not going to have these two separate layers. So when two liquids mix together, and it has to be liquids, we call them miscible. Go back, ethanol and water, since they do mix, they're both polar molecules. Okay, now the opposite, if you take two liquids, like say oil and water, and you notice that they don't mix, they actually just make two layers, then we call that immiscible. That means that they are not dissolvable. And if you remember kind of from earlier on, this would be like the difference between a polar and non-polar liquid, because all liquids would be covalent compounds. Polar and non-polar don't mix like that. Now, the next term is solubility. So what does it mean when we're talking about the solubility of something? Well, when we use the term solubility, we're basically talking about how much solute, like how much salt or how much sugar, dissolves in a given quantity of solvent. Like how much sugar can I put into water? How much salt can I put into water? Okay. Now, this always depends on a certain temperature. And if you've ever made Jell-O, you'll know that you have to dissolve. You're going to dissolve a whole bunch of sugar in water when you make Jell-O. And you can't do that in cold water because the sugar just doesn't dissolve as well. But if you heat up the water, you can dissolve things a lot better. So we heat up the water, we dissolve a whole bunch of sugar, okay? And then as the water cools, then it solidifies and makes Jell-O. Okay? So just another example of what solubility would be is the solubility of NaCl. So how much salt you can put at water. They've got these all calculated. Chemists have gone through and made tables of all of these. So you can look up, how much salt you can put into water. And at 20 degrees Celsius, okay, so you have to state the temperature, because at different temperatures would be more, you can put 36 grams of salt in 100 mils of water. Okay? If I increase that temperature up, I could put more grams. If I lower the temperature, I can put less. Okay? Now, a question over here is, well, what would happen if I put 37 grams in? Well, it says that I can only put 36 grams. So if I decide to put 37 grams in there, 36 of them would dissolve, but then I would have like 1 gram of salt just sitting there at the bottom that won't dissolve anymore into the water. That's what solubility means. Now, kind of related to this was what a saturated solution means. So if you think of like you've been saturated with water, it means that you've been completely drenched with water. So a saturated solution means that you've added all the possible solute into the solution. I've added all the salt that I possibly can into the water, and if I add any more, it's going to not dissolve. So it's when no more solute will dissolve in the solvent. Okay? So basically what's happened is I've added too much. So if you look down here, 40 grams, I add 40 grams in there. Most of it dissolves, but I get 4 grams left over at the bottom because my solution is saturated. Okay? I've put as much salt as I possibly can in there. Now, an unsaturated solution is the opposite. Okay? Is when you still haven't reached saturation point, you can still add more salt into the water and it will still dissolve more. Okay? So just saturated and unsaturated. And finally, we're just going to kind of just leave off or end off with a solid dissolving into liquid. So this is the kind of picture I just kind of want you to look at as I kind of talk here. So what's happening here is right down here is sodium chloride, okay, is salt. So the blues are sodium and the greens are chloride. And it's an ionic compound, so it's a crystal. So why salt dissolves in water is basically what happens is all these little water molecules, okay? So the water molecules, remember, are an oxygen, and then a hydrogen, and a hydrogen, okay? And remember that these, if we are polar, have partial charges to them, okay? Well, what also has a partial charge is a sodium ion. What also has a partial charge is a chlorine ion. So what happens in this ionic compound is the water comes in, this water molecule right here, comes in and uses its partial charges to basically separate out the ionic compound or their ions. So now the sodium is not attached to the chlorine anymore. And that's what's happening over here is basically water molecules are surrounding a chlorine, and then they're also going to surround a sodium, and they're going to prevent them from coming together. And if they prevent them from coming together, they're not a solid anymore, they're not an ionic compound, and that's why things appear clear. Okay? Now, this isn't a reaction. Okay? This isn't water bonding to them. It's really just water just kind of surrounding it, but it's not a bonding. So that's why we remember this when we said that when water dissolves or when salt dissolves, it's not a chemical reaction, even though there is some indicators like a change of color. It's not a chemical reaction because there's no transfer of electrons, and we haven't made anything new. We've just kind of broken things apart. Okay? Now, the next unit or the next topic we're going to have is, well, how would we care about how fast dissolving rates are? What if we want to get this to happen really, really fast? Like we want this tablet to dissolve in water extremely fast. Okay? How do we do that?